All right, so we need to talk about relationships with enthalpy values. So obviously we can't just be testing every single reaction all the time. So it's best if we can either have a database of them all, or we can manipulate them in some way to use enthalpy values that we know to find enthalpy values that we don't know. So there's a couple of relationships that let us do that. First of all, if you have one reaction and you know the enthalpy value, and another reaction is that first reaction multiplied by some value, all you have to do is multiply the enthalpy value by the same number, and you will get the new enthalpy value. If a chemical equation is reversed, so if you have like an endothermic reaction, you reverse it, it's going to be exothermic, or vice versa. So what you would do if you reverse an equation, you just reverse the sign. So a positive would become a negative would become a positive. The last one, if a chemical equation can be expressed as the sum of a series of steps, then the delta H of the reaction for the overall equation is the sum of the heats of reaction for each step. In other words, if you can add up two reactions to equal a new reaction, and that new reaction is the one you want to find the delta H for, all you have to do is add up the enthalpy values for those two reactions. So you see how A plus 2B yields C and C yields 2D. They can be put together so that the C's cancel, and now you have A plus 2B yields 2D. New reaction, so all you have to do is add those two enthalpy values together. So we get something like this. And we want to know the enthalpy value for this top reaction, and we're given these bottom ones. So in the top reaction, carbon's on the left. So in this one, I have carbon, and I have 1 mole of it, just like the top, and it's on the left. So what I want to do to this one is, the top one is nothing. Keep it exactly the same, because it has the same mole ratios and everything's on the right side that I need. This one, the second one, has carbon monoxide in it, which I need, but it's on the opposite side. So I need to reverse that equation. So I'm going to go ahead and make a positive. And also, there's only 1 mole of carbon monoxide up there, so I need to divide this whole thing by 2. So I'm going to go ahead and divide that by 2. And then on the bottom one, we have water, but I need it to be on the other side, and I also need it to be divided by 2. So I'm going to go ahead and make this a positive and divide it by 2. So when I do 566 divided by 2, I get 283, and it's a positive. Then 483.6 divided by 2 is 241.8, also a positive. Then I just add this one, and this one together. So plus 283 minus 393.5. I get a total of 131.3. And that is my delta H value. So it's pretty simple. So there's a couple more practice ones you can do. Practice helps. It might take you a little bit, but the more you do, the better you'll get. So standard enthalpies, since we deal with change in enthalpy, we can decide 0, kind of like altitude. We just measure changes in altitude, really. We base it on sea level. Well, who decided that? I don't know, but somebody decided sea level is going to be 0. And we measure it in relationship to that. We just chose one. So there's 3 parts to a standard. The first one's standard state. So gases are always at 1 atmosphere, and they're pure. Liquids and solids, they're the pure substance in the most stable form at 1 atmosphere and the temperature of interest. But the temperature of interest is usually 25 degrees Celsius or 298 Kelvin. They're the same thing. If it's in solution, then it's a 1 molar solution. Standard enthalpy change is when all reactants and products are in those standard states that were just mentioned in the last slide. And this little degree sign, whenever you see it up here, that means standard. You'll see that with a lot of different variables. The standard enthalpy of formation is the change in enthalpy when 1 mole of the compound forms from its constituent elements in their standard states. For a pure element, it's always 0, and it's also called the heat of formation, because enthalpy and heat, we use those words interchangeably sometimes. So in this would be the standard enthalpy of formation for methane. See how we take the elements and we formed 1 mole of the product? So that's how they look, and then all of the values are in the back of the book in the appendix. So most heats of formation are negative because we are forming something that's more stable, right? We're going down in energy overall. Otherwise, it wouldn't be favorable. So that's why. So with reactions, because we can use the heats of formation, you can take the reactants and we're going to say, okay, instead of forming them, we're taking them apart. So you could use the enthalpy of formation equations and reverse them, which would reverse the heat of formation. And then for products of a reaction, you are forming them. So essentially we're ripping apart the reactants and then forming the products. And then if you take all those equations and put them together, you can actually get the heat of a reaction that way. So what you would do in an equation like this, and I should have my book open, but I don't, so I'm just going to kind of talk through this, and then you can work on the practice on your own. But in a situation like this, we would find the enthalpy of formation, the heat of formation for all of these. Okay, I already know this one's going to be 0 because it's an element in its standard state. But since we're taking apart the reactants, we are going to make this a positive. We're going to reverse that value. Then for the formation of the products, we'll keep that value. So whatever you look up in the back of the book for methane, reverse it. Whatever you look up for the formation of carbon dioxide and water, keep it the same. And also remember that those values are for 1 mole of that substance. So with water, you'd also have to multiply it by 2. Then add them all together, and you will get this value. So, double check yourself, make sure you're doing it right. But that would be the delta H of the reaction. So we don't actually even have to add up other reactions like that. I mean, we still technically are because it's the formation reactions, but that's really all there is to it. So I think that is a good stopping place for now.